All right, in this video, I'll be working through a paper 2 question related to wave physics. And it says, by reference to the direction of propagation of energy, state what is meant by a longitudinal wave. All right, so you should be able to compare and contrast longitudinal waves from transverse waves. Those are the two types of progressive waves that we sort of talked about. And so a longitudinal wave is when the particles move along the length of the direction of propagation of energy that is parallel to it. So I'll say in a longitudinal wave, particles move parallel to the, and then use this language, they say the direction of propagation of energy. So particles move parallel to the direction of propagation of energy. In a transverse wave, you change this word to perpendicular, right? So that's the difference between them. State the principle of superposition. All right, you all might have this in your notes somewhere. You wrote down the principle of superposition. Let me see how well I have committed this statement to memory, being that I'm the instructor of this course. It's kind of like, hey, I should have it memorized, right? Now you all get an open note, pre-AICE open notes, right? But I should know this. And so see if my wording agrees with yours in your journal. Everybody flip to that page if you got it handy. So I'm going to say the principle of superposition is when two or more waves the resultant displacement is the algebraic sum of the displacement of the individual waves. How close is that to your definition? It's what? When two or more waves meet at a point, the resultant displacement is the algebraic sum of the displacement of the individual waves. I misspoke a little bit there. All right, so yeah, at a point, I think this would earn the 2 marks, right? Something like that. So that's the principle of superposition. Waves have to superpose, they meet, and when they do, you add them up. That's how the resultant is. Okay. The wavelength of light from a laser is determined using the apparatus shown. So we're going to figure out the wavelength of this light. Now remember, as the light emerges from the slit, it diffracts, which means it spreads out. Okay, so the wave kind of goes like this, but then there's a wave emerging from here also. And so you get this interference, or like crest meets crest, right? So all the crest meet crest, and so there's going to be like a bright spot right here, and then a dark spot, and then a bright spot again. And again, it's because all these waves sort of propagate, and where the path difference is an integer multiple of the wavelength, they're reinforcing, right? They're constructively interfering and sort of making it bright. And you may recall that the wavelength of the light is related to the distance between these. Hold on, let me do that up there. You may recall that the wavelength of this light lambda is related to the distance between these slits, which is A. That was the conclusion you should report it for your lab work. This distance here we call D. And as I mentioned, there's going to be a bright spot here, and there's going to be a dark spot on either side of it, dark spots, but then there's going to be bright spots on either sides of those. So it alternates, bright, dark, as a result of the constructive interference, the destructive interference, the constructive interference, and so on. So points of reinforcement and points of cancellation. That's what interference is, right? A pattern of points of cancellation and reinforcement. So that's how we observe this pattern. So the distance between, two bright spots is what we call x. And we can relate all of these with the wavelength, lambda equals AX over D. That's why for our lab work, we plotted, distance against X, and therefore A over lambda was equal to the slope. So we could solve for A. We knew the wavelength of our light. Here, I think we're going to solve it for the wavelength. All right, so that's a little overview of the physics there, a little reminder. Let's see what we're doing with it. It says, the light from the laser is incident normally on the plane of the double slit. They give us the separation, they give us the distance to the screen. They tell us the bright fringes, and it says the separation of adjacent bright fringes is 4.3 by 10 to the negative 3. So they actually give us this distance x also. That's right here. So A is 3.7 by 10 to the negative 4. This value right here is x. This value right here is b. And they ask us to calculate the wavelength. I mean, and look, in nanometers too. So it is very straightforward in terms of if you understand the physics and you remember your equations, lambda equals ax over d, how do we solve for lambda? Let's plug in everything. So A, remember, is this distance between the slits, and so it's 3.7 by 10 to the negative 4 meters. X is the distance between the bright spots, which they tell us is 4.3 by 10 to the negative 3 meters. So we get meters squared in the numerator divided by the distance 2.3 meters down here. So our answer as we calculate this is going to be in meters, right? But we want the answer in nanometers, so we'll have to do one more conversion. So let's I'm going to write the answer to this over here. And I kind of know I'm going to roadmap my solution. I know that the answer here is going to be in meters, so I want to convert to nanometers. And I remember that there's 1 billion, 10 to the 9 nanometers per meter, okay? So the final step of the calculation will be to multiply whatever number you get here by 1 billion. Right. Calculator check. Everybody get a calculator. 0.7 by 10 to the negative 4, not 0. Calculator. Times 4.3 by 10 to the negative 3 divided by 2.3 meters gives an answer of 6.92. Okay, it rounds to 6.92. Thank you. By 10 to the negative 7. So multiply that by a billion, okay, and it basically gets rid of those 10 to the negative 7 plus 2 more. So, you know, I'm comfortable enough just saying, well, that's 692 nanometers. But if you still have this number in your calculator, just go ahead and times it by 10 to the 9, and you will see that your answer is, you know, rounds to 692. There's 600, and you might say 690 is a slightly better answer than 692, just because of the significant digits. 2 significant digits here, 2 significant digits here, 2 significant digits here. So it's best to report the answer to the same level of significance. So 690, that's pretty close to red light. Okay, 700 red light, so that's a red laser. That's 690. Now it says the intensity of the light passing through each slit was initially the same. The intensity of the light through one of the slits is now reduced. Compare the appearance of the fringes before and after the change of intensity. Ooh. So we want to connect, why did we have to define the principle of superposition a moment ago? How is that related to this? All right, and so we have light that's emerging from these, you know, slits. Right, and it's moving out like this, and there's light coming out like this. And remember, we're adding up sort of the waves here to give us bright spots. But now we're taking sort of the intensity of one of these out. So let me redraw these waves kind of more familiar like this. Okay, let's say the waves look like that. And before, they were both the same intensity. So we had the principle of superposition meant when this wave meets this wave, you get a double crest and double trough, right? They just add up like that. But now we're decreasing the intensity, okay, of one of the splits, okay? So the light emerging through one of these is decreased. And so the reason why the bright spots were bright was because we were adding them up, right? And we were making them double bright. Well, now one of them is going to be lower, so it's not going to be as bright. So one of the things we can say is that the bright fringes aren't going to be as bright. Likewise, why did we see a dark spot? The dark spots occurred where a wave like this met a wave like this, okay, where this crest met this trough, and so they added up to 0. That's why it was dark, okay, because we perfectly canceled out the intensity of one of the waves. Well, if now all of a sudden one of the waves is less intense, it's not going to cancel out the other wave, right? And so the bright spots are going to get darker, and the dark spots are going to get brighter. Because again, the dark spots exist as a result of destructive interference. We're no longer destroying the wave completely because one of the slits has a lower intensity. Does that make sense to everybody that's following along there? All right. Again, if you have any questions about it, please don't hesitate to sort of stop. You want to say, again, relating this back to that principle of superposition is the way forward. So just try to think your way through it without anchoring your thoughts on a very formal principle of superposition is tough to do. So the bright, now it just says compare the appearance before and after. It doesn't say explain why, which is kind of nice. Like we gave the explanation up here, but they don't ask us to provide that. They're just saying, hey, tell us what's going to happen. The bright fringes get less bright. Okay, they're going to appear a little bit darker because again, you're not sort of adding them up the same way. The bright fringes get less bright, or let's say the bright fringes get dimmer. The dark fringes, the dark places, get brighter. And again, it's because we're no longer perfectly destroying the wave there for the destructive interference. Right, this has been another one of Dr. Slice's work, example paper 2. Wave. We'll see you next time.